welcome to Algebra II with Mr. Clausen. Today I want to talk with you about real-world logarithmic models. And to get started, I want to go over an example involving earthquakes, and then I'm going to talk about a second real-world logarithmic example that revolves around the pH of solution in chemistry. And so to get started, I want to talk a little bit about how earthquakes are measured. We use something that's referred to as the Richter scale. Okay. And all the Richter scale is a logarithmic model. The nice thing about a logarithmic model is that if you take a number like 7.9 for an earthquake that happened in New Madrid, Missouri, what you can do is that you can take relatively huge numbers, right, and make them a lot smaller. You can make them very comparable. So, for example, let's say if we are talking about a level 7 earthquake, something that would be a 7 on the Richter scale, what this is equivalent to is that it is equivalent to the seismic energy of the earthquake times 30 to the 7th power. And so what this allows you to do is if you are going from 7 to 8 on the Richter scale, what you're doing is that you are saying that a level 8 earthquake, or an earthquake that would be an 8 on the Richter scale, is 30 times more powerful than a earthquake that would receive a 7 on the Richter scale. And so you can take very large variations of energy and equate them to really small numbers, which can be very useful. So maybe a fun fact here is, if you're saying that a size 7 earthquake is equivalent to 200,000 tons of TNT explosive, right? Just a little fun fact. What this Richter scale allows you to do is it allows you to say, hey, if a level 7 earthquake is 200,000 tons of TNT, a size 8 earthquake on the Richter scale is close to 6 million tons of TNT. And so if you were looking at something like seismic activity that can go from really small vibrations that you could never feel to huge catastrophic earthquakes, it allows you to very easily compare these values and to elaborate on their intensity. So you would just take the logarithm of 30 to base 30 and do some of the examples like we did last time. Now, since we're actually doing a comparison type question here, which is what I'm going to ask you to do in your homework, we're actually going to leave it in the exponential form. But what I want to point out here is that when you use a Richter scale, it is a logarithmic scale. As you go from one level to the next, you are incrementally talking about a multiplier. From 7 to 8 is 30 times more intense. Okay, so let's say, for example, I want to compare the earthquake in 1812 in New Madrid, Missouri, which had a 7.9 seismic Richter value, and compare it to the amount of energy of the largest earthquake on record in Valdivia, Chile in 1960. And so what we're going to do here is we're going to compare the magnitude of a 7.9 earthquake in New Madrid, Missouri in 1812, and compare that to the largest earthquake on record in Valdivia, Chile in 1960. And so if you want to be able to do this, sure, you could go and quantify it and subtract it out. But the thing is we have some knowledge of rational exponents, and we have some knowledge of logarithmic and exponential models. And what we can do is we can combine those things to answer this question. So as I was saying over here with the Richter scale, if you want to know how much more powerful one thing is over the other, or one earthquake is over the other, we can take the energy multiply it by the factor for earthquakes, and we can say 9.5, and divide that by the energy times the multiplier to the 7.9 power. And so what you're going to see here is that we are just simply taking the total seismic energy of the larger earthquake, or the magnitude of the earthquake in Valdivia, Chile, and dividing it by the earthquake in New Madrid, Missouri. And so whenever you're looking at this, what you're going to see is that E is in both the numerator and the denominator, so we can just cancel it. And then what we can do is we can use our knowledge of exponents, which involve, if you have A of m divided by A of n, this is equal to A of m minus n. And so what we can do here is go 30 to the 9.5 power, subtract 7.9 from that power, and you would have 30 to the 1.6 power. And then what you would find is, after you perform that operation and see how big that number is, you would get 230.88. And what you would find is that the difference in magnitude between these two earthquakes is 230.88. And so what I mean by that is the earthquake in Valdivia, Chile is 230.88 times more intense than the earthquake that took place in New Madrid, Missouri, as far as comparing this example. And so Richter scales, since they are logarithmic scales, you can take two really small relative numbers like 7.9 and 9.5 and relate huge spans of numbers, right? Because if we're talking about seismic energy, something that goes from so small that you can't even feel the vibration to something that would shake a city to its core and leave it in rubble and ruins, can be very much equated using a logarithmic model. And so let's just do a second example. So again, if you're thinking about this, you can think of your magnitude example being something like 30 to the size of the first earthquake you're trying to compare to the second earthquake, and just simply going 30 to the x1 minus x2, and that would give you the ratio, the difference, the change in energy that would occur. So let's do the same thing here, just so you can see a second example. So if we go and we want to look at an earthquake that's a little smaller in intensity, all right, we go E to the 30 to 6.9, and we divide that by the energy times 30 to the 7.9. Okay, and remember the e's would cancel. And if we go and we look at this, we say 6.9 minus 7.9. And what you're going to notice in this given situation is that's 30 to the negative 1 power. And so the earthquake in Kobe, Japan in 1995 was 1/30th the intensity of the earthquake that took place in New Madrid, Missouri in 1812. Okay, so hopefully you can see some of that difference in that relationship when we're looking at this, and how logarithmic models or logarithmic scales can be used to take large variations of data and make it really simple to compare them. So a second example that's very common is chemistry pH. In pH, for those of you that don't know, describes the hydrogen ion concentration in solution. And so we keep track of this because if you have certain foods like yogurts, for example, or really anything with a preservative can be something as simple as a weak acid that is used to maintain a specific pH so that bacteria doesn't grow in it. So when we look at a pH model, you're actually looking at something very similar to a Richter scale model. So the pH scale is pH, which is equal to the negative log of hydrogen ion concentration. Okay, so whenever you see something like H plus in this in parentheses, we're just talking about concentration of hydrogen ions. Okay, so you take that ratio and then it goes and it tells you what the relative concentration is. And so if you want to know the concentration of hydrogen ions in egg white, all right, we're just talking about moles of H plus per liter of solution. Now, one thing you got to keep in mind with pH is it is a unitless value, all right? There's no units to keep track of. Concentration has a unit, but when you take the log of it, you have to just make sure that the units that you're plugging in are correct. And in this given situation, it's nothing that you have to be super concerned about. But in this particular situation, if you want to find the H plus concentration, one of the things that you're going to do is you're going to say 8.0, and you're going to set this equal to the negative log of H plus. Now, I mentioned this previously in an earlier video, but whenever there's no log value indicated here, you're going to assume this is log base 10. All right, and what's really nice about the pH scale is that if we're talking about something from a pH of 7 to 8, what we're actually saying is that if you increase the pH from 7 to 8, that you actually have 10 times less the number of hydrogen ions than you did before. And you're like, what, less? Well, it's because you have the minus sign here. Okay, so as pH gets larger, hopefully you know from a physical science class that as pH gets larger, you become more basic. More basic means you have more OH ions and less H plus ions. Okay, and so one of the things that I want to point out is because a logarithm is a inverse operation to a exponential function, this is log base 10. So what I'm going to do here is just real quickly, I'm going to switch the minus sign from one side to the other here. So I'm going to say multiply both sides by negative 1. All right, and I'm going to explain why I'm doing this in a moment here. So that I get negative 8.0 is equal to the log base 10 of H plus. All right, and I'm going to do something really cool here. So if you have log base of something, I talked about this in my exponential model where I said that y equals bx. So if we look at y equals bx as a exponential model, the logarithmic model is log of b to y equals x. All right, so if you want this to be similar or equivalent, what you can do is you can say that y is equal to bx, or b to the log base b of y is also equal to y. It's b to the power of log b of y. Well, what I'm going to do is I'm going to take log b of y and I'm going to set it to the power of b. And so how do I do that? Well, I can do that by just going 10 to the power of log base 10 of h plus. But remember, whatever I do to the one side, I have to do to the other. So 10 to the power of negative 8.0 equals 10 to the power of log base 10 to the concentration of H plus. And what you'll actually see is that these guys cancel, and then this term becomes isolated all by itself. The y value is what it is equal to. And so what you'll get is if you perform this operation, you'll get 10 to the negative 8.0 equals the concentration of hydrogen ions in this solution. All right, so now that I explained that, let me go through it one more time so that you can see this example again. So this is a relatively basic solution. So if you were to write this out, you could just say concentration of H plus is 1 times 10 to the negative 8 moles per liter of H plus. And so mustard has a pH of 3.6, significantly more acidic. And so we expect the number of H plus ions to be much bigger. So let's do the same thing we did before. 3.6 is equal to the negative log of H plus. Let's multiply both sides by -1 again. Right? If you're comfortable with just switching the negative sign to the other side, that's fine as well. We just can't have the negative sign in front of the log when we're trying to do the base 10 operation. So I'm going to take this logarithm and I'm going to use it as a power to its base, which is 10. So I'm going to go 10 to the negative 3.6 power. I'm going to go 10 to the log of base 10. Okay, and just like I said, since these are inverses, they cancel out. It's sort of like saying 1/2 and multiplying it by its inverse, 2/1, to get 1. All right, that's just with a fraction type situation. So 10 to the power of log base 10 is the same thing as multiplying these inverses together and getting 1, if you need like a kind of a pictorial example to compare that. So then we get 10 to the negative 3.6 is equal to the hydrogen ion concentration, right? Super useful, okay? And so after we compute this out, we can just say, hey, 1 times 10 to the negative 3.6 power moles per liter, or molarity, depending on how familiar you are with acid-base chemistry, is the concentration of H plus in solution. All right, and so this is the hardest type of pH example that you may be able to see. If you get a situation where someone says, oh, I have the pH of acetic acid and the hydrogen ion concentration for acetic acid is, let's see, I'm going to say 1 times 10 to the negative 4.76. Then all you need to do is you need to plug that into the original definition of pH, right? You should definitely have this on your note card. And we can say that the pH is equal to negative log of 10 to the negative 4.76. Oh, and keep in mind that this is log base 10, so we're asking how many times does 10 go into this number? Well, it goes into that number, negative 4.76 times. All right, and since this is a negative, the pH of acetic acid is 4.76. And boom, you would just have the number. So with that said, I hope that you found these two examples helpful and that with this you have a better understanding of logarithmic relationships in real-world applications. And with that said, let's do some math.